Okay, so good evening, everyone. Let's start today's lecture. So welcome to week 12 of Advanced Prediction Models. I'll start with a few announcements, and then we'll get to the course content for today. So use the discussion boards. I think there's not been much activity for the past few weeks, but if you have any questions regarding lecture content and so on, please use the discussion board. And also try to give feedback on the lecture after this class. So for this lecture, this is the Google forum. Assignment 2 grades are out, so I hope some of you or all of you have checked your scores that you've gotten. Okay. Any complaints about that? Okay. So the grading for the exam would be done in a couple of weeks. So hopefully we are targeting a date which is the date of your project final report submissions. And after this date, you can come and check your scripts if, in case you have questions about if you have not gotten what you were expecting to get. Okay. And grading will take into account the length of the question paper and the difficulty level. So I had sent out a feedback form about some remarks. I was seeking some feedback about how the exam was, and so some of you have replied. I think about 25 students have given some feedback. So 50% of the class has given some feedback. So based on that, we will appropriately make the assessment for the exams.
What was the general feedback?
So in terms of length, people were divided. So out of 25 odd responses, I would say like 13 people said it was not lengthy, but about 12 people said it was lengthy. But in terms of difficulty, everybody felt it was difficult given the time constraint. Especially because the questions need you to read the questions, which may have a lot of text there. That time eats away into your time needed to respond to the answers, right? So I think, the feedback form is still open. You can give feedback on anything that you found interesting to share. Okay, so in terms of the project, as we discussed at the beginning of the class, there's going to be presentations during the lecture hour, the lecture time on April 26th, which is in 2 weeks. So groups can also participate in, I think there's a student exposition. I don't know what the right name is there, but there is a student exposition on April 28th afternoon. It's with other master students, other undergraduates in CVA. So if you want to participate in terms of showing your project work, basically giving exposure to the business analytics program to variety of audience. It could include employers, it could include other general audience. So if you want to participate, just send me an email. And as I said, project report is due on a couple of days after your presentations in case you want to do some last minute changes. And also a second point about course evaluation, your feedback on the lectures. I've tried to ensure that there is a feedback link for each lecture. So some of you have kind of replied for each one of them, and you've also replied for the assignments and the exam as well. So that's quite helpful to kind of change the course of the content and so on, right? So similarly, there will be a overall class feedback which will be sought, I think, from next week onwards, not by me but by the department or by the college. So you'll receive an email, and I think you've been given 2 weeks to respond. So there's this typo from the previous slide. Actually, previous slide is fine. Okay. Now a little bit more details into the project logistics. Please refer to the instructions on the project instructions PDF that I shared earlier. as we just said, the presentations will be in class. Each group will get 7 minutes because there are about 20 odd groups and all of them should present. There will be optional Q&A. So Q&A is not really a requirement here because everybody kind of knows the techniques used and so on. The number of content slides should really be less or equal to 5. So you really want to focus on presenting something interesting. So you can't spend 5 minutes just describing your data set, right? What did you do would be very interesting to hear for all the rest of the audience as well as by me. You need to upload the presentations to the course website by 5 p.m. on that day because it's 7 minutes and there's going to be fast turnaround. I will try to manage the time, and if I have all the presentations beforehand, I can do that effectively. If there's a demo component, contact me before the Monday so that I know that there is going to be a demo component and so on. Do not exceed the time. And so the general tip is to focus on the insights, some of the design choices and why things worked and why things did not work. Not just things work and things did not work, but the why part of it. And don't just focus on the performance, because the numbers, unless you can tie the numbers back to some higher level business goal, it's not very meaningful by itself. Okay. Any questions regarding all the administrative things that I've been speaking about for the past 8 minutes? Any questions?
All the group members have to give the presentation.
You can divide, or you can have one person give. But I think it's a good opportunity for all of you to kind of practice and give your part of your presentation. Okay, so the timeline is these are all the topics that we've covered so far, and I think on week 09 we looked at online learning. So we're going to continue off that thread. We're going to refresh our memories on what online machine learning was, and then we're going to discuss reinforcement learning. And so today's lecture is going to be introductory, so we'll kind of spend more time on motivating why this is a very interesting topic to study, and then we'll just discuss maybe one algorithm related to reinforcement learning. Okay. So that's the agenda. So today we're going to look at have a look at multi-arm bandits and contextual bandits. So these were part of your exam. So I'm guessing that some of you may already know majority of these topics. But then we're going to discuss the motivation behind reinforcement learning and some basic jargon used there, and one of the algorithms called Q-learning. Okay. So let's start with review of online machine learning. So the gist was as follows. So optionally we get to observe. So the online part is so there's a for loop. So it's like at every time step we optionally get to observe the state of the world. It could be a user coming to our website or something like that with their user profile, and then we need to take an action. For example, to show a news item or something which is interesting to the user. And then if it is interesting, we get some feedback signal or the other in the same instance itself. For example, they spend a lot of time on that article, or they click on certain interesting links on that article or something like that. And our goal is to optimize feedback. So since the feedback signal, let's assume the signal being high is positive. So let's say we want to maximize that feedback signal or maximize that reward by appropriately choosing our actions. Okay. And one of the key assumptions in this, at least under this heading, was that the agent's actions do not, agent as in our action of what we do. Let's say we wanted to show for this user a particular news item, has no influence on which user comes next. Okay, that's you can think about whether that assumption makes sense or not. For example, in the online setting, on the internet setting or not, but that was the assumption. So we went through a little bit about the system perspective for one of the applications. This was the MSN.com, which kind of, I guess, shows personalized news articles for visitors. And here the setting was user arrives at the website with their browsing history, maybe they even have a user account on MSN and previous visits and so on. And then the agent here chooses a bunch of news stories to show, and then the user responds by clicking on certain things, looking at different navigation. So you can track all that. And then the goal is to choose action. So in this case, action is going to be to choose content to yield some desired user behavior that you set at the beginning of time. And as I said, the assumption is that recommendations to one user does not affect the other users. So maybe another user comes after 1 minute, then that user, again, you can get to choose what you want to show, and they'll give you a response or a rebound signal on whether they like that content or not. Okay. So in reality, the way they have actually deployed it is users are essentially represented using a feature vector, which includes demographics and some history, and then there are editors for this, I guess, this web property who handcraft 50 chosen articles, and you somehow get the feature vectors for these articles. And then given these feature vectors, given these 50 articles, you just want to somehow figure out a policy which can show, which can figure out a ranking between these 50 articles, and then you get to show maybe 10 of them or 20 of them to the user based on their feature vector. So, and then how do you figure out this rank list of basically which action to take is essentially which 10 of these 50 articles, let's say, that you want to show is through some policy, so through some directive. If the user is a student, then show these articles. If the user is a working professional, then do show these articles. If the user is a senior citizen, show these articles. That could be a policy. Epsilon Greedy part is just you want to perturb those policies such that you can learn new, better policies. So that's the decision service, or this is the online machine learning component of it, where you kind of iterate or kind of perturb the policy so they can learn better and better policies, right? And then you get feedback, and that you kind of use it to improve your policies, right? So in MSN's case, they have these types of statistics. They have 10 million plus users and some number of requests. So by doing this operation where they do exploration, they use the feedback signal to improve the policies and so on, they incur some overhead, and also they update the model. Model is just the updating the policy. So so these are the actual on the ground statistics of how they have deployed this policy improvement online machine learning system, and they claim that they have observed some relative gains post deployment of the system compared to previous state of affairs. Basically, their measure goal was to increase the number of clicks, and so they have seen that there is an increase in clicks. So that's the application that we looked at. So yeah.
On the previous slide, so what does it mean if this squiggly graph is going up and
It's
down?
just a function of dates, right? So you can think of, I could have just shown you an average number. Like I could have just shown you one number that before the system was deployed, there was some base rate of clicking, but now after the system is deployed across all contexts or across all different user types, they're seeing an increase in some performance measure.
So same policy was used across all these days, and then
No. The policy can change, right? So once you deploy the system, the system has the opportunity to kind of change its policies. So it starts with some policy and it can improve it, right?
So is it possible that some of the days the policy was not good or something like that? Or,
I mean, they're showing that it's not bad. I mean, relative improvement over a day is 25% on average. Yeah, it could be. It may not be good. So the number of requests that are coming per second is in thousands, right? So so there are many users who are coming per day. So it could be that for some users you're doing really well, for some users you're not doing that well. But the users are basically represented as contexts, these states or contexts, and then some sort of a contextual policy. So given this context, show these articles. Given some other context, show some other articles. Would be a policy, and they kind of improve that policy even every 5 minutes. Okay. So that was the application, but to get to the contextual version of it, we discussed a more elementary version of this problem called the multi-armed bandit problem, where the problem was there is no context. So at every round, a user comes, the user doesn't reveal their context, but you are trying to choose an action. For example, the same as before, you can choose some news items, and hopefully they will click on the news item or not. Right? Maybe there are links in the news item, they'll click on those links or not. Right? So the interaction is just this. So you want to pull an arm. Pulling an arm is essentially taking an action. Oh, these are the articles I want to show. Is pulling an arm. Or you can say these are the other set of articles that I want to show. That is pulling another arm. Right. So arms are essentially these sets of articles that you may want to show. Or in this case, I have given which ad or color to display and so on. And the reward is going to be some measure of success, which is similar to before. And by the way, this is not just based for internet running example. It's also actually this whole problem came from the field of clinical trials in healthcare. But I'm just using this web internet news recommendation personalized website as a running example. So the formal setting.
Pulling an arm is what we are showing the options of news articles to the user, or user making the choice?
No. We are the agent. We whoever is the owner of the personalized news website. So we pull an arm, what we show, and they respond by giving us a reward. So they, as in whoever else who's not the agent. So these are, I mean, you just call them as the environment, right? I think we use that terminology. Yeah. So the formal setting was if we had k arms and each arm corresponds to an unknown distribution mu k. Let's say the distribution support is between 0 to 1, which just means that the rewards are normalized. It's just for convenience. So at each time the agent pulls an arm. So I decide to do something, right? I show these articles or some other article out of one of these k arms, and I observe a reward, which could be a number of clicks, or I mean, it will not be number of clicks because it's between 0 to 1, but some other measure of reward signal. So in each round, I'm going to get this number back. I pick an IT and I get back a number xt, right? And it's going to be a sample from the corresponding distribution new subscript IT. So IT is just an index, right? 1 to k. And the objective is to maximize the expected sum of rewards. The expectation is over. If you are randomizing, then the expectation is or in terms of your randomization as well. If you're not randomizing, then the expectation is over these new case, right? And so in terms of notation, mu k is the expected reward that you can get if you pull an arm k, and the best arm is going to be just mu star. You just sort the mu case and pick the one with the highest value. So that's mu star. And so why we are defining this is to kind of concretize the notion of what is the goal here. The goal is to maximize the expected sum of rewards, and we're just going to rewrite it in a slightly different way in terms of regret. But regret is just the same as maximizing rewards because this term is a constant anyway. So just backtrack a little bit. It is an online problem, and so we need to come up with strategies or ways to pull these arms. Right, that is a policy. So policy is now it's a very trivial policy because there is no context. So it's just asking, figure out something that you need to do in every round. Okay, pick one arm which has the highest mean reward. Ideally, if you knew all the distributions, you would know the mean rewards, and you just pick the arm with the highest mean reward. Right. So that's a very trivial policy, but you want to figure that out. Okay. So how do you figure that out? You can try all these arms in different ways and figure out which one is the best. So in terms of evaluation, I said we want to maximize the expected cumulative rewards, which is this term, because these are the numbers that I'm getting in n rounds. But we sometimes use the notion of regret, which just means that what is the best thing you could have done if you knew the best arm, right? So this is what you could have done in every round. You would have gotten this much reward in expectation, but you're getting XTs as rewards in each round. You can take expectation over here, so you can replace this XT by new subscript. Okay. And one of the algorithms that we saw, very intuitive algorithm, was the Epsilon Greedy algorithm, which just says at each round t, with probability 1 minus epsilon, pick the subjectively best arm, which just means there are some yellow pluses here, but ignore them. So it's basically saying with probability 1 minus epsilon, just whatever information that you have about these arms, let's say you had some information, pick one of those arms. Sort them and pick the one arm with the highest value, highest empirical reward, let's say you're maintaining. Or with epsilon by k, pick a random arm. Okay, basically pick any arm at random. That's the exploration. So yeah, so this algorithm, it's very simple and it actually works fine. It has good performance guarantees in terms of regret that you can show. And I think I use this word Epsilon Greedy even in the MSN personalized case study in one of the diagrams. So basically they're improving policies by doing Epsilon Greedy, but that problem requires context. Here we don't have context. So that's the slight distinction here. So is this algorithm clear what it's trying to do? Right. How many of you have studied Epsilon Greedy for the exam? Okay. So I mean, at least the intuition should be clear. It's just trying to split time. So and every round is basically flipping a coin with probability 1 minus epsilon. Let's say that's the bias. If it lands heads, just use the arm which has the highest empirical mean reward that I know so far. If it lands tails, then pick a random arm. Take a random action. If you take a random action, you'll still get to know something about that action, right? This is the exploration part where you will at least learn something about an arm, and this part is where you'll learn something about an arm, but that happens to be the best arm only, right? So that's the intuition here. So next, we looked at a slightly more sophisticated algorithm called the upper confidence bound algorithm. So it's not that involved. It's still doing something similar to Epsilon Greedy, which is that it's in every round it's picking an arm, which is the maximum over a bunch of numbers for each arm. So for each arm, you are just assigning a number, okay, in every round, and the arm that you're going to play is just going to be the arm with the highest number, okay. And so these numbers have to be determined using whatever you've done so far. So let's say you tried a few arms so far, then you can, for each individual arm, you can compute the empirical average reward, right? So that's going to be this new hat term. So if I've tried arm 1 3 times, then I'll have an empirical average of what is the mean reward for that arm, right? An empirical average reward for that arm. If I've tried arm 2 for 5 times, then I would have another number, right? So I would have those numbers. Those are just determined easily. These numbers that are attached to the arms are just an additive version of them. So I'll just use the empirical mean reward. I'll just add a term which depends on which round I'm in and how many times I've tried the particular arm. So it's basically trying to balance the idea that if I have not tried an arm, so this essentially a bonus term is gonna be high, and so this final scalar that I assign to that arm is going to be high, and so I will try that arm. And if I have tried a particular arm many times, this bonus term will be low, and so hopefully if the mean is high, only then I'll potentially pick that arm. If the mean is low, I will not pick that arm. That's the intuition. How do you clear this? Figure that out. Okay, so the third algorithm that we looked at is called the Thomson Sampling algorithm. It's a Bayesian algorithm for multi-arm bandit problems, and it works as follows. So you'll assume a uniform prior. Let's say you'll assume a uniform prior on the parameters. So what are the parameters of the multi-arm bandit problem? The parameters are the mean rewards. I mean, of course, there's a distribution for each arm, right? So there is let me use I for, so there's k arms, and so there is this mu I, so which is a mean of a random variable which is distributed. Let's say x is distributed according to mu I. Then the mean of that random variable is this. So those are the parameters of this of the multi-unbalanced problem, right? So you're gonna assume a prior on the on this. Okay. So the mean can be, I mean, since I just said that the random variable support of x, so x can only belong to 0 and 1, so clearly the mean can also belong to 0, 1, but I don't know where the mean is. So I'm going to assume a prior distribution on the mean. So I'm going to maintain a distribution. I think we use notation pi. So I'll call pi I0 a distribution on mu I. So mu I is now a random variable. Previously there was no Bayesian interpretation, mu i's were just the means, they were parameters. Now they become variables. So the variables, if they become variables, then they'll have to be supported by a distribution, right? So that's pi I, and I'm going to keep change. So pi I of 0 would be the prior, which I'm calling, let's set it to be a uniform distribution, and pi I of t would be the posterior distribution for this variable mu I at the tth round, okay? So basically I'll have a distribution. I keep modifying the distribution as I see evidence, as I see data. And so how would I do that? If I have a prior and if I have a model for how the data transpires, then I can just use Bayes rule to compute a posterior distribution, right? So if I have these posteriors at round t, then Thomson sampling says, okay, you have a posterior for the mean rewards for all the arms. Just sample a number for from each of these posteriors. So you'll have k samples. So these are all scalars, right? Just sort those samples and pick the arm corresponding to the highest value. It's a very non-intuitive way of determining which arm to pick, but it turns out that this way of doing the sampling and picking the highest arm, the arm with the highest sample value, kind of ensures that you do exploration and exploitation correctly, and this algorithm also ensures that eventually you will figure out the arm. You will be pulling that arm with the highest mean reward. Okay. Is the algorithm clear? Yeah.
How does it ensure that in the previous algorithms you looked at both the distributions that have the maximum mean,
Yeah.
as well as randomness, both were incorporated into this.
Yeah.
But here
it is incorporated, so you can think of pi as being a distribution on the means, right? You don't know what the true mean is, so pi I of t is supposed to be a distribution on the true means. I mean, what could be the true mean, right? So pi I of 0, let's say there are two arms, let's say, so pi I of t, pi 1 of t can be something like this, which just says that the maybe my mean is closer to here than here, right? And the second one, pi 2 of t, let's say, is still uniform, let's say. You haven't tried the term, so it's uniform, let's say. Then the mean can be anywhere. So you sample one number from here, one number from here. If you sample a number from here, it will most likely come from here. And if you sample a number from here, the expected value is somewhere in between, but you don't know, I mean, you can get a number from anywhere. So you compare those numbers and try one of the arms. So that kind of ensures that you do exploration and exploitation. So for example, if this was not uniform, if this was concentrated like this, then you know that you're going to sample something from here. And so you will play the arm with the high amount of probability mass, right? You will play this arm because you get a sample, then that sample value will be higher than this guy, and so you are playing the arm with a potentially higher mean reward. Right?
that means always depending on the context. Already you collected some data.
Yeah.
And
so the data is already encoded in this pies.
Correct.
These are posterior distributions. So you had prior, which was uniform. You would somehow compute the posterior using Bayes rule, and we'll discuss Bayes rule in a couple of slides. But if you had the posteriors, then you just sample from them and compare the two numbers and play the number with the highest value. So actually, this can be reinterpreted as playing the arm with the highest posterior okay, this two steps can be interpreted as playing the arm with the probability of being with playing the arm with whose probability is okay. So whose probability okay, so since these are all random variables, it's basically play that arm I whose so since these are now random variables whose nu I is greater than nu j for all j not equal to I. So it's basically this probability. How is this computed? This is computed on every pi. I mean, this is going to be a joint distribution or all pi I t's pi. So I don't know. Can you understand this? So this is if you had a distribution, posterior distribution on every arm, I can always compute the probability of a random variable greater than another random variable. Right? It's like I have two Gaussians. I can always ask what is the probability that Gaussian 1's value is higher than Gaussian 2's value, higher than Gaussian 2's value. That will require me to use both Gaussian's distributions, right? Similarly, for every arm I'll have a pi I of t. I can compute this probability of nu I greater than nu j for all j. So this is not just one inequality. I want the probability of this event where this random variable is greater than every other random variable. Okay, and if I compute this for every I and pick the so this will give me a number, right, between 0 and 1. So I can pick that I for which this number is highest. So this is a non-sampling way of describing those two steps, but it's not necessary. Intuitively, if you understand what I'm trying to say, if you have high posteriors will concentrate over the true means. Will concentrate closer to the true pi's, and if those pi's are higher, then hopefully we'll sample from there. That's the exploitation, and because they're sampling, there is some exploration also going on. That's it. Okay, so we'll just take a brief detour into conjugate priors because I said you can compute. So this is a prior. So when I say a prior and posterior, it's a prior distribution, a posterior distribution, right? Now we're going to look at just one-dimensional distribution. So think of a Gaussian or a uniform distribution or a beta distribution or something like that. We'll actually describe them in more detail. I said you can use Bayes' rule to kind of go from a prior to a posterior. So now we are maintaining actually distributions, right? Whereas in the UCB algorithm, we were just maintaining one number per arm. In Thomson sampling, we have to maintain a distribution, right? So how do you represent a distribution in a computer, right? If it's a uniform distribution, you just represent it by the end values, right? You don't really have to explicitly say the value of the PMF. If you had a PMF, then you would need for every support value its probability mass. So there's this question of how do you represent distributions, and conjugate priors are a nice way of representing distributions without doing messy integrals. So if you look at Bayes' rule, especially with continuous distributions, you will actually have to do integration. Okay. So remember Bayes' rule. It was it's a probability of some theta given data was probability of the data given theta. Right. It's actually integration of probability of yeah. Okay, overall theta. So this is basically, I mean, this is just a joint distribution, so I might as well write the joint distribution, which is just probability of B. This is the denominator is just a probability of B, right? So this, to compute this is a marginal, so you really have to do integration if it's continuous distributions. If it was not, then remember from graphical models, you were just doing some summation here and so on. Okay, So instead of doing explicitly doing base rule, conjugate trials, the notion of conjugacy with respect to distributions is as follows. If you have a prior distribution, let's say, and it belongs to it looks like this: p alpha of theta. Alpha is just a parameter of the distribution. Okay, so if this is the prior distribution, it's said to be a conjugate to a model to a family of distributions p subscript capital theta. So just think of one element in there. So p subscript theta. So p alpha of theta is conjugate to a likelihood model p theta if you employ base rule. So let's say base rule is you're computing the posterior probability of theta given data, which is going to be the prior, which is that thing over there, times the probability of times the likelihood of the seeing the data given the parameter, right? This is just a likelihood model. Divided by this integration that I was talking about, you integrate over all possible values of theta. Okay, so that's just base rule. You can ignore the product here if you want to. It's not consequential. So this is base rule, and let's say you got some posterior distribution. If the posterior distribution also belongs to the same family of distributions, then this is called conjugate to the likelihood model. Okay. So is this concept clear? So I think in the 2 weeks ago we had discussed beta Bernoulli as a conjugate pair. So where beta distribution is this distribution, the Bernoulli distribution is going to be the likelihood model, and then the posterior is also going to be a beta distribution. So you really don't have to do any integration. There's a simple update for going from the prior being a beta to a posterior also being beta. So there's a simple update of just the parameters. There's no integration that's needed, and that's the whole point of conjugate priors business. So you can do base rule without doing the spending a lot of effort computing the posterior. So I think in the previous slides I described last week's slides I had Thomson sampling part in the slide. So let me just briefly go over it. So we say that so theta, which is k-dimensional, we say that theta follows distribution. Is the multi-dimensional. So theta is a random vector now. So the random vector follows a Dirichlet distribution, which means that the support of this distribution is going to be a simplex. So simplex is just a triangle in 3D. So simplex is this. So let's say 0, 1, 0, 0, 1, and 1, 0. It's basically a triangle. So that's a simplex. If you can visualize the three-dimensional object, it's basically like a plane cutting the three canonical axes at these points. I'm just showing the stuff in the first quadrant because that's what it is. This just means that the values of u are positive, so you only concentrate on the first quadrant, and the sum of the values is equal to 1, which you can see, right? Sum of values is equal to 1, and any point on this triangle will have a sum of the values equal to 1. Okay, that's all it is. So Dirichlet distribution is just a distribution over all these points. So for every point here, I can attach a density function. Okay, so that's what Dirichlet distribution is. It has a slightly messy notation. What is the probability of a point? So alpha is going to be the parameter. What is the probability of a point? It's just like Gaussian, right? You can ask what is the probability of x given mean is equal to something, variance is equal to something. Similarly, what is the probability of this random vector given the parameters? And it has an ugly expression, so we don't need to parse that. But pictorially, how does it look like? So as I said, let's think of in 3 dimensions. Okay. So let's say theta is 3-dimensional vector. Then theta is going to be a point on this triangle, and you're just trying to put a distribution on top of this triangle, right? Just like in 1 dimension, you will have a distribution on an interval. In this although it's a three-dimensional thing, since it's a plane, it's essentially two-dimensional. You can think of a distribution on top of this triangular area. Okay, just like you would visualize Gaussians as in 2D as being, I mean, Gaussian support is going to be infinity, so you can just think of them as contours, right? If you look at the top view. So here, Dirichlet distributions look like this. It's basically again some probability mass over triangles. Okay, and these why do they look different? Because of the parameters. The alpha determines how the distribution looks like. Just like the mean and the variance of the Gaussian determines how the Gaussian looks like in 2 dimension, right? So anyway, that's the intuition for Dirichlet distribution. So the reason why I'm bringing up Dirichlet distribution is because if you just have 2 parameters in the Dirichlet distribution, then it is the beta distribution, and beta distribution with parameters 1, 1 is the uniform distribution. So we are just talking about a slightly general distribution, okay? But I just want to say that this Dirichlet distribution, this is let's say that is the prior, then that distribution is actually a conjugate prior to the multinomial distribution. So what is the multinomial distribution? Multinomial distribution is has again 2 parameters. Actually, it's written here. A multinomial distribution is a distribution over a vector. Let's say the multinomial distribution is over a vector of k coordinates. Okay. Then the multinomial distribution will have 2 parameters. Let's fix the first parameter to be 1. Okay. That just means it's a categorical distribution if you know about it, but don't worry about it. Don't worry about the first parameter. So what does the multinomial distribution do? It basically says which coordinate of z can be 1 or not. Okay, so it's basically your notion of multi-class. If you had k classes, then it's basically this random vector is just representing the one-hot representation of which class is going to be on and which class is not going to be on. Okay, so let's say you had 3 classes: cats, dogs, and humans. Then if you think of this multinomial distribution z, okay, it's going to be a 3-dimensional vector which can take values 0, 1, 0, 0, 0, 1, and 1, 0, 0. Okay, there are only 3 values that z can take, and multinomial distribution is just saying with what probability can this be true, what probability can this be true, with what probability can this be true. It's just a discrete distribution. Okay, so this, let's say this means that the class is dogs, this means class is cats, and this means class is humans, and this is just a PMF on 3 outcomes basically. So that's the multinomial distribution with the first parameter equal to 1. Okay. If the first parameter is not 1, then slightly different interpretation, but let's not go there. So what I'm trying to say is that if so this was the multinomial distribution, and we just described the Dirichlet distribution, and the interesting thing is, let's say you drew n samples of the multinomial distribution, n examples, okay, and now you want to apply the Bayes rule. Let's say you're prior on the parameters. So multinomial distribution has a parameter theta. Okay, it's a k-dimensional parameter. Since it's a PMF with in 3 dimensions, there's going to be 3 numbers here, right? Of course, there's redundancy. One of the numbers is redundant, but if z is k-dimensional, then there will be k parameters, right? So you can think of, and further, since these parameters are actually probability distribution, they will lie in this triangle, because we just said that the Dirichlet distribution support is all points whose sum is equal to 1. Right, so it's actually a distribution on distributions if you really think about it. But so if you think of the prior on the multinomial's parameter to be Dirichlet, and multinomial itself is a likelihood model, then the posterior probability over the parameters is just written this way, and this is just the Bayes rule, right? This is just probability of theta given data is the probability of, it's the prior probability of theta times the likelihood of the data given the theta divided by the probability of data. Okay, and you can actually explicitly write down, you can substitute these expressions for p of theta and p of z given theta, and see that this posterior is also is proportional to theta to the power something. Okay. Now, if you look at the expression for Dirichlet distribution, which was in the previous slide, you would see that the expression of Dirichlet distribution also is very similar. It's theta to the power something. Okay, so you can hand wave and say at this point that this is also actually a Dirichlet distribution. okay, because it has a functional form which is a product of bunch of thetas to the power exponents, okay, and that's why it is also a Dirichlet distribution, which means that the posterior distribution of the parameter given data is a Dirichlet with these parameters, okay. So that's a general expression of the beta Bernoulli. So multinomial, if you think of just two outcomes instead of three, that would be a Bernoulli distribution, right? Heads or tails. Here I said heads, tails, and something else. That's why it's three-dimensional. So beta Bernoulli that we saw two lectures ago, is a special case of Dirichlet multinomial conjugacy, and it's a very useful trick to use if you don't want to deal with messy base rules integrations in your computer. Okay, you can make these assumptions about your data, and you can get the posteriors for free by just doing additions. Okay. Anyway, so that's the tangent for Thomson sampling, because in Thomson sampling we had to handle priors and posteriors. That's why I discussed the conjugacy properties. Now let's get back to the multi-arm bandit problem. So why do we have to actually assume that the parameters, that the rewards are actually drawn from a distribution? Why do I have to assume this news? Right? Why should there be a distribution for each arm? And further from one round to the next round, why should the rewards be sampled from these distributions in an IID manner, right? Can we draw these stochastic assumptions? Was the question. And that's because these rewards may be the output of a complex process, right? It need not. So when a user comes to a website and sees a particular news article, it's not like they're flipping a coin with some bias and telling you that it's a good article to see or not, right? The environment. They may have some complex procedure going on in their minds, and so they give you a reward signal. So you can't really sometimes make a stochastic assumption about how the rewards are generated. And it could also be that the rewards are generated by an adversary. Somebody who absolutely hates MSN.com, let's say, comes on MSN.com, gives a feedback, then still you want to perform close to what went to such a bad user. Okay, so basically you don't want to make assumptions about the randomness in terms of the reward process, right? For example, if it's an adversary, they may give a 0 reward for every page with every article that you show. Okay, so that's not random. So you may want to even include such responses, such reward signals from the environment. Okay, and so that in fact we can actually drop the stochastic assumption, and so that means that we are now not going to talk about distributions about the environment at all. So there is not going to be any new eyes. But our algorithm can have randomness, right? And we'll see Exp3 algorithm which maintains weights on the arms, and therefore unpicks a arm drawn from that PMF, and therefore our algorithm is random. But there is no randomness on the environment side. Okay. So what is going to be the template? So adversaries. So we can't make the adversary completely adversarial, in the sense whatever action we pick. The adversary can always say it's a really bad article to show. Okay, so that means that the adversary is very powerful. So we're gonna restrict the adversary by saying the adversary should pick the rewards that he or she is gonna suggest for every action that I take in round T, independent of what I do. So they pick a bunch of rewards a priori. For that round, so they'll designate a bunch of each one number per action or arm that I'm potentially going to pick. I'll pick some arm, and they're just gonna let's focus on the binary information case. They're just gonna reveal the number that they had picked before seeing my suggestion, right? So that at least restricts the adversary. So that I mean, think of the alternate situation where I pick an arm and then they say, okay, that particular arm I'm gonna give a 0 reward or a negative reward. That's too powerful, right? There you can't do any learning there. So in this setting, we saw an algorithm called the Exp3 algorithm. Okay, and again, this algorithm, let's just focus on the intuition. The intuition is that we initialize for every action we assign a number again. Okay, and these numbers are now going to be as follows. So at the beginning of time, we're going to assign number 1 to each one of the arms. Okay, and then at each time t, I'll somehow use these numbers to create a in my mind, in the agent's mind, a distribution which just means that I'm going to normalize, right? So W divided by all the W's that I've assigned for each of the arms. There is a slight modification where I want to add some, I guess, exploration, like you saw in the Epsilon Greedy. I was doing with epsilon by k probability, I was picking a random arm, and 1 minus epsilon probability, I was picking a best arm. Similarly, I'm just adding some additive term, but this basically is just a normalization of the weights that I'm maintaining for each arm. Okay, and what are these weights? How I'm gonna accumulate them? We are in a bandit setting. Okay, so in every round, after I play an arm, let's say I play an arm, then I'm gonna update the weights for each one of the arms. Okay, but you can ask, I don't have any signal for any of the other arms that I did not try, right? I'm gonna create a signal, a feedback signal for every arm, and how am I gonna do that? The feedback signal is going to be for the arm that I tried, which is let's say I try the arm I subscript s in round s. If I try that arm, then I'm going to take the feedback signal, that the raw feedback signal that I got, I divide by the probability with which I picked this arm, and if I did not pick the arm k, which means that all the k minus 1 arms, I'm just going to take the reward signal to be 0. So, which means that I just created a reward signal which was scalar to a vector reward signal, which is k dimensional, and I can update these weights for all the k arms, right? So this is it. This is the update equation, and with these weights I can normalize them and create a probability mass function, and from this probability mass function I can draw an arm and play that arm in the next round. Right? So this is the Exp3 algorithm, and it works for any instance and without making any assumptions about how the environment is, right? Whether the environment is stochastic, whether the environment is adversarial, it doesn't matter. This algorithm will work in terms of performance, in terms of the cumulative regret that we were talking about. Okay, it's the same performance measure. I mean, the performance measure has to be changed because now there's no stochasticity in the environment slightly, so the expression kind of slightly changes. But otherwise, it works in the sense of it minimizes an appropriate notion of regret in the non-stochastic setting, non-probabilistic setting. Okay. So that's the algorithm. So we started with MABs because, or multi-armed bandits, because it was kind of, we wanted to get the idea of that even if we don't have context and we have, let's say, k actions to choose, we still have this problem of figuring out which of the k actions that we need to figure out. And we may spend time by just trying out each action. Let's say if I try each action 10 times, okay, and so there are k actions, so I can do 10 times k rounds. I can figure out some empirical value and then just play the arm with the highest empirical value. That's also an algorithm, but such an algorithm can fail with a constant probability. So it could be that after 10 rounds you would have figured out the empirical mean to be of a second best arm rather than the best arm, and so there's a possibility of failing, and Epsilon Greedy, Thomson Sampling, UCB kind of take care of that issue. Right. Now, MAB is not enough because there's no context, first of all, and there's also the second thing is that there is no carryover effect from one interaction to the next, and this is where we're gonna talk about reinforcement learning very soon. So, do you understand these two shortcomings for multi-armed bandits? There is no context, so you're just trying arms. There's no policy. Policy is just always show an arm k, let's say k star or something. That's the policy. And the second issue is there's no relation between one round to the other. So in one round you kind of, let's say your site crashed. It has no influence on the next round rewards that you may get. If your site crashes, maybe there's a ripple effect and people stop coming to your website and so on. That is not being captured here at all. So that's the shortcoming. But on the ground, it's not used much in industry, although it can do better than A/B testing. So A/B testing is the age-old method where you just split your incoming users into two parts, expose them to two variants of your actions, let's say, in the A/B testing version of it, and then after some amount of testing, after some amount of time, you just do a two-sample hypothesis test to figure out if A is better than B or B is better than A. Okay. So okay, let's get to the notion of context now. So just to, I mean, this is the same slide as before. We remember that users arrive at msn.com with some context. So this browsing history, user account, previous visits, and so on. So we want to use this context. So let's look at how we're going to do that. So for that, we graduated from the multi-on-bandit problem to a contextual bandit problem. So in the contextual bandit problem, in every round we get a context. So context is this description. It could be a vector. It could be a JSON, object which just says, okay, this person is a student. This person has been a student for the past 2 years. Has been a visitor, frequent visitor, or some information like that. And now policies make sense. We want to find the best policy, and the policy is now going to be, for every context, tell me what is the action that I should be doing, right? And we may not see the same context twice. Context can be vectors, in which case they are vectors in a vector space, so you may not see the same vector twice, right? Yeah, the difference from MAB is the presence of context. And so what is the point of context, right? I mean, context just complicates the problem. One naive way of solving the contextual bandit problem is, for every context you think of it as a multi-on bandit problem, right? For every context, I just instantiate a multi-on bandit problem and figure out the best action to do in that context, right? But then that is very inefficient, because first of all, contexts need not be finite, and even if they are finite, you're not really using the information that for the same context, policies can suggest the same action. So we want to use the idea that policies are maybe lesser than the number of contexts. So even if contexts are infinite, I may only have 10 policies, which means that I can figure out information about other policies when I play one policy. So we'll see that through this example now. So let's say we have 5 ads. Okay. So these are the actions that I can take. These are ads, not news articles. But let's say these are the 5 actions that I can take. And let's say we have 4 policies. And I'm not going to explicitly detail the policies. Let's say there are 4 policies. For example, one policy can be, if the user is a student, show by pet lizards. Okay. So some context dependent suggestion, right? What action to take. Basically, this map context to ads. So now let's look at one round of Exp3, where we now ignore policies, okay, and where we now think of policies themselves as arms, right? We can always ignore actions and talk about, since we have 4 policies, and since I wanted to figure out the best policy, I can always think of policies as my arms. It's like it's like a meta algorithm where I don't care about the actions, because the policies will determine the actions, but I care about which best policy to pick. So I'm going to try these policies over rounds, and hopefully some policy will be the best. I'll figure it out using Exp3, let's say. So how does it work? So in round T, let's say the policies make the recommendation as follows. In round T, E1 says choose add A2, E2 says, so E's are going to be the policies. I have 4 policies, and each policy is suggesting some action, right? Which is not relevant to Exp3 itself, but I'm just saying what actions they were suggesting. Okay, one of those 5 actions. Say Exp3 chooses arm1 because it was maintaining the weights, and then it did a random draw from that normalized weights step, and the random draw happened to be play arm E1, which means play policy E1. Okay, and say E1's add choice A2 was clicked. Okay, and E1's add choice A2 and it was clicked. So basically, I'm just trying to say there is a response for the action that E1 policy took. Okay, then what would Exp3 do? It would assign a reward x tilde, which would be the raw signal that I got. If it's a click, let's say it's 1, then I would just divide it by the probability with which I picked that or that policy E1, right? So that's the Exp3 algorithm, and rest of the arms will get reward 0. That was the definition of going from one reward signal to getting a reward signal for all the 4 arms in this case, right? And the benefit of context is as follows. We can do better because E2 also recommended A2, right? E1 recommended A2, we chose E1, so Exp3 chose E1, and which means that we should add A2. But if A2 was clicked, we also can infer something about policy E2, right? If we had chosen E2, that would also have recommended A2, and it would have been clicked. So that's the information that we're not capturing when we translate these rewards to numbers on the policies with Exp3. Okay. Basically, what we are trying to say is that we should better estimate the reward for E2 and not just set the reward to be 0. Okay. So formally, what's happening? The world produces some context. So I'm using context X subscript T here. The learner chooses some action A subscript T, and the world reacts with some reward R subscript T. Okay. Now, the regret is very similar to before. Regret is just going to be there is a best policy. Okay, some policy pi. Let's say pi star. I'm gonna sum over all the rewards that I can get by showing all these contexts from 1 to t by using that policy pi star. That's the first term. So it's inconsequential to us because we don't. I mean, it's just a benchmarking thing. We don't have access to it. It's just asking what would you do as an agent? In every round, I see a context. I play an action AT, and so this is the reward that I'm getting, right? Over t rounds. So the algorithm is that we're going to suggest is going to be very similar to Exp3 with that twist that we talked about, because Exp3 is not accounting for other policies which suggest the same action. We're going to do that, and that's called the Exp4 algorithm. It's actually quite old, 27 years old. So the algorithm is going to be as follows. It's again going to maintain a weight for every policy, similar to what I was saying, Exp3 algorithm. And for every round, you're going to observe a context, right? Since I'm maintaining weights for every policy, I can again compute this normalized number, which is just the weight for a given policy. Okay, so the normalized number is not going to be a number over policies. It's going to be a number over actions. Okay, so if I have 5 actions, then I'll determine induced distribution over just actions. Okay, it's not very different from finding a normalized finding a PMF over policies. It's a slight variation. But once I find probability over actions, I'll do the same. Draw an action from that distribution and play that distribution. And updates of the weights for every policy is going to be for the policy which suggests the same action. I'll get the reward signal. I'll divide by the probability with which I took the action, and I'm going to multiply here. I mean, it's the same as doing the summation in the Exp3 algorithm. And if that policy did not suggest this particular action, then I'll just keep the same weight. Okay, it's basically Exp3 with all policies which suggest the same action getting their weights updated. Okay, so that's contextual bandit. One candidate algorithm for contextual bandits. It's a very computationally inefficient algorithm because I'm maintaining a weight for every policy. So if I have like 10 decision tree policies or something like that, then it's okay. But if I have a million policies, which is potentially possible, then it's not a computationally efficient thing to do. There are other algorithms which can deal with computational issue and so on. Okay, but it's a sound policy in the sense, sound strategy of maintaining weights on policies and so on, because it will do well in terms of that objective measure that we discussed. Okay, but as a lead to reinforcement learning, even contextual bandit formulation is not enough. Why is that? That's because if you think of a multi-round bandit problem, this is what we were doing. Every round we were choosing an action, we were getting a reward, and there was no relation between one round to the next. Right? What I do for one user has no relevance for what I do for the next user. Okay. In fact, I'm not even taking into account users' information here. Right? Okay. That was the limitedness of multi-round bandit problem. In the contextual bandit problem, I was getting information, state or context of the user. Based on that context, I was choosing an action based on the policy that is represented as pi, and because of that action and because the user had a certain state, I would get a reward R. Okay, the reward can actually depend on the action that I took in a given state. That's all I'm trying to say here. But again, this had the shortcoming that you get a reward, you took an action, but that has no consequence on the next state that you're going to see. Okay. So let's say in this round I saw a student profile come into my MSN website, I suggest some news article, okay, and I get some reward. In the next instant, somebody else comes, let's say a working professional comes. So the working professional is going to be the profile, right, or the state that has no relation to the previous profile, which was the student, and what action sizes is suggested to the student, right? There is no relation there. But that's not always the case. The more, I guess, a more general version of the problem where you take into account that your actions influence who's going to come next. Okay, so that's the additional loop here. So it's the same as contextual bandits, except that your actions not just determine the reward, your actions also determine who's going to come next. Okay, so that's the so the states or contexts are not going to be exogenous, in the sense they are not determined by some exogenous random process, random or not, some process. Here the actions determine what's the next context which is going to come. Okay, that's the reinforcement learning problem. Any questions so far? I kind of repeated in some gory details things we saw 2 weeks ago, 3 weeks ago. Any questions? Yeah. Yeah.
How would you say that you can perform better when you update the second contact? It may not be one treatment and how would you increment?
It's actually, these are not contexts, these are policies. So we are kind of completely obfuscating context, in the sense whether it's a student or, so for example, let's think of a situation where whether it was a student or a working professional, there were 2 policies which are suggesting MP3 player. Okay, now only if the student came and let's say I picked this policy and the student liked that suggestion. Okay, you can also update the second policy, which was for which was also suggesting an MP3 player for the working professional as well, because okay, not, sorry, that's not the right analogy. What I'm trying to say is, let's think of 2 policies which for a student, both policies are suggesting an MP3 player for a student, but both policies are going to suggest 2 different things if it's a working professional. Okay, so the policies are different because for something else they are suggesting something else. Some other context they're suggesting something else, but for a student they're both suggesting the same. Now it so happened by, let's say, Exp3 or Exp4 that you picked the first policy, okay, and it suggested the MP3 player and it got a good feedback signal. Now that information can also be used for the second policy, although the second policy is going to suggest something else for a working professional compared to the first policy. For the student it's suggesting the same thing, so you can transfer that information for this second policy. Do you understand? Okay. So let's go to introduction to reinforcement learning. This part is going to be light, so people who are sleeping can wake up, because we're going to look at some videos which try to motivate reinforcement learning problem, and then we'll look at some of the basics after a break. So reinforcement learning. So I just happened to, I get a copy of MIT Technology Review, physical copy, but it just so happened I was googling for reinforcement learning, and I saw that this month's or previous month's version or edition has the 10 breakthrough technologies of 2017. Okay. So you can see some of the breakthrough technologies. So these are the 10 breakthrough technologies of 2017. So you can see reversing paralysis, self-driving trucks, I don't know, paying with your face, quantum computers, I don't know, 360-degree selfie, a few things. But one of them is actually reinforcement learning. Okay. That's interesting, right? So we're going to actually study something which is one of the top 10 breakthrough technologies, at least by this particular magazine. Maybe it's credible or not, but one of the breakthrough technologies. So actually these guys rated, I think, deep learning as a breakthrough technology back in 2013. So the first part of the course that we studied is actually not recent. It's 4 years ago, right? but this part of the course that we're going to look at is actually very recent. It's just this year's breakthrough technology. So I'll give you some examples of what has been done with reinforcement learning. It's not just reinforcement learning. There's also deep learning and other new techniques involved. The first interesting piece is this RL agent called AlphaGo, which was the I guess the front page, the cover page of this very famous journal called Nature. So AlphaGo was this RL agent by Google DeepMind, which is this British flag here, and this is Lee Sedol, who was the #1 player in Go. Go is a very complicated game, impractical to solve by a rule-based computer program. So you can't really write a program which can beat the human player by writing a bunch of rules of how to play. Okay, but this particular RL agent was able to beat the player in 5 games, 4:1. Okay, and it has improved quite a bit since I don't know, last year or year before. Oh, okay. Whenever that was. And a second interesting glimpse is playing Atari using reinforcement learning. So I don't know how many of you actually have played Atari games. How many of you have actually played Atari games? Okay. So here's a snapshot of a few of the games. I think 50 such games. And for all these games, DeepMind again, the company developed a single RL agent architecture, which included some deep learning stuff that you have seen, some CNNs and so on. A single architecture, no hand tuning of the parameters, and the same agent was made to train on these all these different games, and it could, I think, out of 70% of the games, it would beat human level performance. Where human level performance is just they got an expert player, and the player also played with some scores, and so they saw how the RL agent could play, and it got higher scores. Okay, I think I showed this particular video on the first class. So this is one of the Atari games. It's called Breakout. So at the beginning, the agent. So RL is all about trial and error, right? Just like multi-arm bandits and contextual bandits, it's all about trial and error. You try something, you get a reward signal whether you did well or not, and based on that, ultimately you learn policies. So in RL also you learn policies. So this is they're showing how the agent is progressing by trying out this game and trying out different policies. Policies just mean what's the state of the affairs and what is the action that I need to take, whether I need to move the paddle left or right or and so on. Okay. Okay, so that's Breakout. But so other than DeepMind, some other people have also tried other things. So Flappy Bird, how many people have played Flappy Bird? Okay, so this is actually somebody got the game engine, which is one version of it is open source. It's probably not there on the Play Store and iOS Store and so on, but so they trained this particular RL agent, which was hooked up to the game engine, and the actions, I guess, is basically clicks, right? I think when you click, it just goes up. The bird goes up. So they design an RL agent which gets the context. The context or the state is going to be how far the bird is from the cubes in the front and how far is it from the ground and so on. And based on that, whether the agent should click the front screen or not. And it learns, basically. It learns a few things. It fails. It sees a score and it improves. Okay, and now this is actually interesting. This is actually, can you guys recognize this game? Yeah, this is Doom. Okay, so a few months ago, some researchers even applied an RL agent for. So this is a play by an RL agent. So applied an RL agent to play this game as well. So going from the 2D games that we saw in the first two examples to this one, and and they have some lot of tips and tricks to get the whole system going, because there is this whole 3D aspect to it, and how do you process the screens, because the agent also sees the same thing as what a human agent human should see, right? It can't it can't be given too much of at least the measurements. It can be given too much of computation, but that's a different matter. And the last part is this car by I mean, there are many self-driving cars which are already being tested at advanced level. So this is a demo by NVIDIA at CES 2017. So CES, I guess, is Consumer Expo, Electronics Expo Showcase or something like that. So this is a demo by NVIDIA people. So I guess they focus mostly on vision-based measurements of things in the front, and then steer the car. There are other many other initiatives by Google, Uber, Mobileye, BMW, even all the traditional car manufacturers are working in this. So I don't know if you noticed, but there was no driver in the car. So so that's possible because of some reinforcement learning component in there. Maybe not for the NVIDIA version of the solution, but definitely for some other solutions. Okay. So in terms of where does reinforcement learning fall in the map, it has relations to optimal control and engineering. So if people have done electrical engineering, they might have done control systems. And so in control systems, one of the subtopics is called optimal control. So reinforcement learning is related to that. It's related to machine learning and AI. That's our perspective. It's related to neuroscience and psychology of how our brain works, or how organisms work in terms of feedback signals, right? And it's also very relevant to economics and operations research, because in OR and economics we sometimes solve multi-stage decision-making problems, like a multi-stage inventory control problem or something like that. And they also have some close ties with, those problems also have some close ties with RL. Okay, this is just a snapshot of same thing, applications. But one caveat is that RL so far requires experiencing the environment many times. Okay, so you really have to make the agent have access to the environment. In this case, let's say the Flappy Bird's game engine, or the Atari game simulator, or or roads. You really need to the agent tries actions, right? Just like we saw in multi-armed binary setting or the contextual binary setting. So it really needs access to the environment many times, and that's because it's a trial and error based approach, and so it's impractical for many complex tasks. So it's not a very general purpose tool yet, but hopefully, I mean, when they said it's one of the 10 breakthrough technologies, they were saying that it probably is a key component of self-driving and so on technology. So for example, like for AlphaGo, AlphaGo had this much computation to beat this one person. So in terms of computation requirement, even at the game level, there's a mismatch of resources, right? So there's a training issue. There's also the resource issue, even in real time when you want to deploy. Okay. So any questions about these applications of reinforcement learning? Okay, so what we'll do is we'll take a break for 5 minutes, and then we'll get into the we'll get into the basics, and we'll end with the Q-learning algorithm. Okay.
There's this one recently I was looking at reinforcement learning. There was a guy who trained a model on Mario, Super Mario, and they ran the whole game. It was really interesting because he was visualizing the learning process and how, like, every action gets different weights over time. It's really interesting. Really interesting.
Yeah.
Yeah.
Games is a good domain because you have access to simulators.
True.
We should start a self-driving initiative at
You
the
know,
university?
so my friend just turned down on he works at the NLP lab, and so he's doing his PhD, but it's very interesting stuff. He's always talking to me about cool stuff. So he had an internship offer from NVIDIA,
Okay.
and he would be working on the self-driving cars, mostly on the communication with human agent to
Yes.
a car that's driving and so on. Really cool stuff. He ended up accepting something else somewhere with Samsung actually, but it's really cool stuff.
Yeah.
The problem is, I love this stuff, and what you realize is, without a PhD, no one will ever let you touch this stuff.
Why not?
I went to BMW.
You can buy a small scale kit, right? You can buy an RC helicopter, and you can just rig the RC part to
It's
your
actually a
computer.
good idea.
People do that with drones. With drones, people do that as long as you have permits and
I'm
stuff.
going to start working full time, get that drone money, and then I'll.
Drones are not expensive. I mean, as a hobbyist, you can do it. You can't do it
Right.
probably on. You need a bigger team to do it as a full-time thing. But
Absolutely. Plus, I'm pretty sure you can't do it without a PhD.
no,
I feel like really. I don't know. I felt like I went to.
PhDs for just trying out what works next, right? With the given technologies, tinkering, you need just an engineering background.
Yeah, because I remember I went to the career fair when I went to the BMW, stand.
Yeah.
They had this big thing on machine learning. I was like, all right, this is cool. I walked up, and they basically said, you don't have a PhD? Yeah, so we're not even going to basically look at your profile.
Large corporations have bad HR practices, but you can.
Hopefully, yeah,
Yeah.
we'll see. It's cool stuff. Thank you.
Yeah, it's just
So okay, we're going to resume with whoever is left in the class. Yeah.
For our final presentation, we have our project is supposed to be like we're classifying our audio, right?
Sure.
So we also want to do a demo, but since we only have 7 minutes, do you think it's better to just screencast like a demo and just play it in class better than like do it live because we're gonna screw up?
Sure. Yeah, works. Okay, so we're going to resume because to get to all those accomplishments that we saw in the previous few examples, ranging from self-driving to playing 3D games and so on, it requires some understanding of how to get to that stage, right? What are the algorithms backing those powerful applications? So we look at the basics first. So what does reinforcement learning address? What does the reinforcement learning framework address? So reinforcement learning addresses a version of the problem of sequential decision making. So it has very similar ingredients to what we saw for the contextual bandits algorithm. Sorry, by contextual bandits setting. So we have an environment within which an agent takes actions. Right? These actions are basically which adds to show or to steer left or right and so on. And these actions influence the future. And so this is the key difference between this setting and the contextual bandit setting. And then the agent gets a feedback signal. And so because the actions influence the future, it need not get an immediate feedback signal like the way we were seeing in the contextual bandit setting. So we may get a feedback signal which is potentially delayed, right? So for example, you're taking an action which is studying today and giving an exam today, you will get a feedback signal 2 weeks from now. So, right? So there's a delay in the feedback. So, and your actions also influence the future in the sense what you study today can influence how much you have to study tomorrow and so on, and how you perform eventually in the exam, right? So the goal is again the same, similar to what we saw earlier in the online machine learning setting. We need to select actions to maximize the total reward collected. Okay, whatever is meant by the total, whatever it could be over a period of 10 rounds, it could be forever, and so on. An RL framework, within the RL framework, you can provide some sound answers to this question. Okay, so what are the ingredients? Let's think about the ingredients first. So there's this environment. So what does the environment do? It sees the agent's action capital A subscript T, and based on the action, it generates the next context. So when I say an observation, it's the next context of the next state as T plus 1. Okay, so there's this relation between the action that you take and the context that you see in the next round, and it also generates a reward RT plus 1. Okay. So look at, there's a slight gap in this index because I'm taking an action at AT and I'm getting a reward in the next round T plus 1. Okay. So t index is time, and the current observation st is called the state, okay, or the context. Yeah.
So in the example we saw, the game, Atari game.
Yeah.
So if the paddle we consider as the agent, so
Yeah. So
So
somebody
what
is
is
playing
this?
that game, so that's the agent.
so what is the state?
The state is going to be how does it look at any given point of time. It's the frame. It's the screenshot.
Okay, so the brick
That could be a
structure
state. There could be other states, but other descriptions of state. But yeah.
So the current brick structure and everything.
Yeah.
as
How
it is,
does the
that
brick
is
structure
what's-
above look like? Where is the ball
Okay.
at any? Like take a snapshot. Take a photograph. So that's the state.
And then st plus 1 would be from the past experience.
Maybe from there. Maybe given seeing that you moved left or right. Okay. Because of your action, probably not much is changing, but at least in that time scale. In the next round, in the next frame, can be a ball moved a little bit more down. Okay, that's a new state. But you can imagine states changing because let's say the ball was here and you were right below it. So in the next state, the ball bounces back. So that's a new state where the ball bounces back and hits other bricks. We'll actually get to this interpretation again. We'll see some examples. And so we also assume in this framework that the future, so the future is going to be the future states or the future measurements that you see at time t plus 1, t plus 2 and so on is independent of the past, which is t minus 2, minus infinity to t minus 2, t minus 1, given the present state. Okay, given the present time, there is no relation between, in a sense they are not dependent. Everything is captured in the current state, and this you've already seen, and it's called the Markov assumption. Okay, so the probability of seeing a state t plus 1 given the current state is the same as the probability of seeing state at t plus 1 given the whole history of states. Okay, and in fact given whole history of states and also given the history of actions that you took. Okay, and we'll also assume that everything relevant is observed. There are variants of this problem where you may not observe some parts of the state. For example, when you see when you're capturing let's say a car through a camera, you may only observe, let's say, the position of the car from which you infer the velocity or something like that. So you only observe positions in different frames of your camera feed, but you can but that's only partial aspect of the state, right? The full state of the car can be the acceleration at that point of time, the velocity at that point of time, and the current position at that point of time, right? So it could be partial, but we'll assume that everything relevant is observed. The agent is going to, what does the agent do? The agent observes RT plus 1 and ST plus 1. And of course, not just T plus 1, but the agent observes basically this tuple of states and rewards. Okay, and these are not going to be independent or identically distributed across time. First of all, they're not going to be independent because there's this Markov aspect, there's a Markov chain aspect to it. And they need not be identically distributed, right? In some other state, there could be some other transition probability into future states, and from the current state to next stage, there could be a different probability distribution. So these conditional probability distributions can be different. So that's why it's not identically distributed. So we'll get to the details of what I mean by IID again. So the agent's objective, as I said, is to maximize total reward. So we're gonna explicitly say that the agent's objective is to maximize this reward, where expected reward, where the expectation is over all the future rewards, where I'm just going to add a discount factor gamma. Okay, this is just a general form. You can think of gamma is equal to 1. It just means that I'm just focusing on getting as much reward as expected reward as possible from now to forever in the future, right? And the key thing is, as I've been repeating, to repeatedly trying to differentiate with this, with the contextual bandit problem, is that your action is going to affect what you're going to see in the future, and therefore that dynamic is that closed loop or that feedback is what is going to influence how you're going to collect rewards. So you may take an action which may lead to a future state where you cannot collect any good rewards anymore, right? So that's what I mean by this feedback aspect to the problem. And so you may want to trade off, for example, the current reward to gain more rewards in the future. Okay, and you can see this in games, for example, where you may want to not get the immediate benefit by doing some long-winded thing so that you can get a much higher reward later on. Okay, in games you may have to do that. So what exactly is reward? Reward is a scalar feedback signal. So I'm representing it as a R subscript t. It basically indicates how well the agent is doing at step t. But that reward signal may be a consequence of some actions that you took long time ago as well. But it just tells you, it gives you a number. It's a feedback signal at round t, but it can be a consequence of things that you did some time ago as well. Okay. So reinforcement learning is based on the reward hypothesis, which basically is that all goals can be described as maximization of expected cumulative reward. Okay, it's just a hypothesis saying that if you can tell me a goal, if I can formulate, I can formulate it as a maximizing an expected cumulative reward, and therefore I can apply RL there. Okay, and again, what is the goal? The goal is to select actions to maximize total future rewards. They are all related, right? So this is actually just more philosophical. It's just saying that if you can give me an abstract problem or an application problem, I can define, and if you can define a goal there, I can define an equivalent cumulative reward version of it where I can focus on just maximizing expected cumulative reward. Okay. As I was saying, actions may have long-term consequences and rewards may be delayed. And I guess this is a repetition. We may want to sacrifice immediate reward to gain more long-term reward. Okay. So what is happening pictorially? So the agent is getting a state similar to contextual bandits. We are getting a state and a feedback signal. Okay. In contextual bandits, this was the context and this was the reward signal, and we're taking action. That action is going to influence the next state, and the action is going to influence the next state. So that's the jump from contextual bandits problem. Okay. Similarly, so basically what I'm saying is in every round you'll have basically three objects that come up: the state, the reward, and the action. Okay. So it could be that the action that you take at time t, the reward that you get at the end of time t or at the beginning of time t plus 1 is rt plus 1. Okay. So this repeats again and again. So if you look at some other machine learning settings, so what is the big difference? There is no supervisory information. So feedback signals need not be, for example, class labels. In supervised learning, you make a prediction, you get a class label, right? So here the feedback signal can be anything. So reward signal is more general. Feedback can be delayed. Time matters because things are not IID. In supervised learning, you make an assumption that there is no relation between the test example that I see now to the next example I see next round. Okay, and agent's action affects subsequent rounds. But in terms of information, unsupervised learning is when you don't get any supervisory signal. Reinforcement learning, you get some supervisory signal, but that's in terms of the feedback signal. In the online, this is an online machine learning problem. And supervised learning, you get full feedback signal whether you made the right prediction or not, right? Because you know the ground truth. You know the class labels, for example, in classification. Or pictorially, this is what's happening. There's inputs which are features. You get a training signal which actually tells you the target output, and you make some output. So hopefully these two are similar. In reinforcement learning, you get some inputs. So these can be contexts or states. Based on that, you're taking some actions, so it's more general than supervised learning. These actions, kind of affect the environment, and that influences the next input that you see in the next round. And the environment also tells you the reward based on the actions that you took. Okay. So pictorially, that's the a difference between supervised learning and reinforcement learning. There's also this notion of exploration exploitation, which we saw in the multi-arm bandit problem as well as the contextual bandit problem. So again, what is exploration and exploitation? Exploration is to find more information about the environment, and exploitation is whatever information I know so far, try to exploit that to take actions, right? So that problem is still there, just because this is very similar to contextual bandits with rounds tied to each other. Your action is influencing next context, basically. Yeah, that's what I'm written here. So RL is also, you can place it in the context of sequential decision making settings. So there are let's say two types of sequential decision making problems. RL is going to address the first version where the environment is initially unknown. So in the sense, if an agent is acting is trying to drive a car on the road, it doesn't know anything about what's good, what's bad. So it has to do trial and error to figure it out. by basically by interaction, and the agent improves its policy by figuring out what is the right set of driving maneuvers to do. That's different from planning. So planning is also a sequential decision making problem. Okay, so what is planning? Where you know everything about the environment. So so you know that if you are in some state, if you take this action, where you will go next. Okay, so the dynamics of the environment are completely known. Okay, and the agent just has to do thinking, as in the agent just has to do computation. It knows the dynamics of the environment. It's at the beginning of, let's say it's in some state. It just needs to figure out what is the sequence of actions to take so that I get total reward. When I know the complete dynamics of the system, okay, I know everything about the environment. So that's called the planning problem, and planning or reasoning in AI. And this problem is, I guess, simpler version, right? Here we don't know the environment. Here we know the environment. Even if you know the environment, planning is not an easy task. But now that we don't know the environment, it's an even more difficult task. Okay. So RL framework, or typically when you design an RL agent, it involves one of these three components or more. The components are going to be a policy, which is going to be the agent's behavior function, which is very similar to what we saw in contextual bandits. A policy is just, given a context, what action should I take? Okay, given a state, what action should I take? Now there's going to be a new object called a value function. Okay, a value function is going to be a number that I attach to each context or each state, which tells me how good is that state. Okay, it's a goodness number for a state itself rather than a number for a nice goodness number for a policy or an action. Okay, it's a number that I'm going to assign to a state itself. Okay, and the third object is a model, which just is a model of what is the dynamics of the environment. How does my action in this state make me go to a next state? Okay, there was no dynamics in contextual bandits, right? The next state was exogenous. It could be random, it could be adversarial, whatever. Here there's going to be a model of, okay, if you're in this state and you take this action, there is a possibility that you'll end up in some other state, right? And that's kind of evident in the examples that we saw. If you're doing self-driving, let's say you press the accelerator, the next state is kind of related. Given that you accelerate and there's an empty road and you're in state something, then you will reach state something else. You can have a model like that. In RL problem, you just don't know the model of the environment beforehand, of how the environment will respond to your actions. In the planning problem, you will know that. So again, what is a policy? Policy is a map from state or context to action. A deterministic policy is going to be, give me the context, I'll tell you the action. A stochastic policy or a random policy would be, given a state, I'll have a distribution over actions. Okay, if I have k actions, then I have a PMF over k actions. So I can draw an action at random and play that action. Okay, it's just a generalization. So let's look at a very simple environment. So let's say this is the environment. So it's not even, okay, this is the environment where an agent has to go from here to goal. Okay, and so what are the states? The state is just going to be the agent's location. Okay, state is just going to encode is the agent here, 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 here. So just the XY coordinates, let's say. And at every state, the agent has possibly 4 actions. At some states, they may not have 4 actions because they may hit a wall on one side. And the reward is going to be independent of action and state. It's going to be -1 per time step. Every time it's just a constant reward of -1 till you reach your goal. Okay, and so to maximize this reward is basically saying try to get to the goal as soon as possible, right? That's how you can kind of get the least number of negative ones, right? So what would be a policy? A policy would be at every state, what should I do? So pi of s. So a state is going to be one of these blocks. So pi of s will tell go right here, go south here, go west here, and so on. Okay, that's a policy. What's a value function? So this is a slightly newer object than what we saw in the contextual bandits and multi-arm bandits. So a policy is a value function is a prediction of the future reward, and it's used to evaluate the goodness of state itself, goodness of the context itself. Okay, and it can be used to select between actions, but we'll get to that. So what is a value function? So let's fix a policy pi for now. let's say we're in state S. Okay, so a value function ascribes a scalar number to the state, which is going to be the expectation of all the rewards I can get starting from this state and following policy pi. Okay, it's just if you implement this policy and I'm starting from this state, what is the rewards that I collect? Because the policy is going to tell me the next actions, and the actions influence the next states I'll land. Potentially they could be stochastic or deterministic. Because I'll land in some different states, I'll get some reward. Again, my policy will tell what to do in the go to the next state. Again, I'll get a reward and so on. So this is the number of how good the state is. Okay. Yeah.
Is that enough, or should we compute with respect to all the policies?
For a given policy, this is a number for every state. What do you mean by computing this for all policies? Yeah, we naively, if you can compute this for all policies, then you can pick the best policy in some way. We'll get to that. But for a given policy, also computing this is tough, right? I mean, this is an expectation operation. So you actually, for a given policy, you can, if you had access to a simulator, you can keep running the policy. It's going to be a Markov chain. I mean, you have seen Markov chain in previous lectures. So it's going to be a Markov chain. It's going to collect a bunch of rewards. You can average all the rewards. I mean, sum them up and take an average, like a Monte Carlo average, and that will give you a goodness of that state for a given policy. So you can compute this for every state for a fixed policy. And you can change policies and also compute this. Now, what will you do with that is up to you. So, what were you thinking here?
What I'm missing here is you are applying in the previous the gain problem that we showed. Start to go.
Yeah.
So if you apply, if you calculate the V pi for only one policy, you will not follow the same policy all through. You may change your policy along across the road. So
we will change the policy. So this is a policy. If you flip an arrow, one of these arrows, that's going to be a different policy, right? How will you do that change? We have not yet gotten to that part yet. For a given policy, we can ascribe numbers to every state. That's what I was showing here. We will discuss how to change the policies and how to improve, because then, of course, these numbers are no more valid, right? That's a different policy. Yeah, we'll get to that. So let's see how to ascribe these numbers. You can see that if you're at goal, if you're a state right next to goal, then the value of that state is going to be -1, because you can just see that. I mean, there is no, first of all, there is no expectation. There is no stochasticity. If you take what is that, the west east operation here, then you'll get to the goal. So you're one state next to it. So the value of that state is -1. Do you agree? I mean, based on this this policy, this is a policy. It's telling you from here go east. Okay. So if you do that, I mean, if you're in the state, you know that you will get a constant reward of -1. So that's the R. So there's only one term, and you terminate. So there is no infinite. There is no summation there. Whatever is the summation length. And similarly, you can go back, and these are going to be the values basically of that policy for a given fixed policy. It's just an intuition of what is meant by value. So being in the state is less valuable than being in the state, right? Because that's what it intuitively means to ascribe this value number to every state.
how do we get the -3 number? That's no easy.
The policy is fixed, right? The policy is saying at that position, do something, go down.
Okay.
The policy is fixed, so you just add numbers in this way, basically.
So policy is not just go east. Policy is the complete east.
Oh yeah. Policy is a complete. For every state, it tells you where to go. Yeah. Policy is not just one action. Yeah. Yeah.
What is a gamma?
So gamma is just a discount factor. It's used in case there is no, there's no termination. In some environments, there is no termination. You keep on going. So if you keep collecting rewards, then you will reach infinity, right? If you have possible. Huh? Yeah, I mean, so yeah, if there are loops, for example, then you will keep circulating around it and keep collecting rewards, and you may run to infinity. So gamma is just a number typically less than 1 to ensure that this summation is constant. If you assume that each of the r's are bounded, then if you keep gamma less than 1, then the summation is going to be constant. Okay. But it's not needed in this example because there's only finite, finite number of, you can't really go in loops. Okay, so the third object, which is just a model, and this is also new from the contextual bandits problem, is going to be what does the environment do next? And so that is captured using this notation script P and notation script R. So P is going to be what is the probability that the next state is going to be S prime given I'm in state S and I'm taking action A. Okay. It could be probabilistic, it could be even deterministic. Okay, it could be a deterministic function which says if you are on the road and you take, let's say, brake action, you're going to stop. Right. That's the there's a deterministic thing potentially. So it may not be probabilistic, but in general we are saying that if you are in state S and you take an action A, you will reach S prime with this probability. You may reach S double prime with some other probability, and so on. So that's the dynamics of the world. And also rewards, we can say rewards also are random, and if you are in state S and you take an action A, then the expected reward is going to be script R. Okay. You can make them random, but they can be deterministic as well. Like in the maze example, I was just saying that it's deterministic. In fact, for every A and S, it's just going to be -1. So that's also a candidate reward. Okay. So this like rewards were -1, right? At every place, irrespective of state and action. Okay. So that's why I didn't have to write many reward equations or explanation tables or something like that. So dynamics is going to be how actions change the state, and we just assume that if the policy says left, then you just go left. Deterministic dynamics. So there's nothing stochastic here. Okay. But you could add stochasticity. You could say go left, or sorry, go east, and then it doesn't go east with some probability. That could be incorporated in the environment, right? Sometimes you press the joystick left and it will not go left, things like that. But that's the model. Model just means what is the transitions and what is the rewards, how are they modeled, okay? And so based on these objects, policy, value function, and model, there are different types of RL agents that you can design. What I mean by RL agents you can design, these are going to be agents as in programs which will compute policies, right? Which will try to compute good policies so that they can collect cumulatively, the cumulative total reward, expected reward is going to be high. That's what these agents are programs are trying to do. So a value-based agent will try to manipulate the value function. Policy-based will try to manipulate the policy, right? Very straightforward. And there are some other variants which kind of capture both a policy function, try to manipulate both policies and value functions to get to best policy. So I'm not telling you how they're doing it yet. We're going to look at how they're going to change, how they're going to get to a good policy. And there are also model-free and model-based algorithms. Model-based ones try to kind of estimate the model of estimate the dynamics of the world, because if you are in state S and you take action A several times, then you can kind of empirically get a distribution of where you will land next, right? That would be a approximate model of how the world works. So you can kind of estimate that and use that information. And model-free just means that you don't do that. You don't kind of keep an estimate of how the world works because it's just too complicated, right? So those are the three objects and how the agents are divided. So before we get to the algorithm, which is going to be Q-learning. So Q-learning is going to be a very simple algorithm. I can just explain it in 5 minutes. But before that, let's just go through what we already know, Markov chains, add some rewards onto it. It's going to be called a Markov reward chain or a Markov reward process. And then we're going to add decisions into it, and then it's going to be called a Markov decision process. Okay. So we're going to start from what we already know to something called a Markov decision process, and that will give us some intuition about the one algorithm that we're going to see about reinforcement learning today, which can be explained in 5 minutes. That's going to be Q-learning. Okay. So let's do that. So let's start with Markov chain. Okay. So what is a Markov chain? A Markov chain is basically saying if you're in state S, it just describes what is the probability of going to some state S prime. Okay, it's just a conditional distribution of if you're in state S, what's the probability of going to some other state, and so you can represent it as a transition matrix, right? Just as we discussed several lectures ago. And so every row is going to be, if I'm in state S, what's the probability of staying in state, if I'm in state 1, what's the probability of being in state 1, what's the probability of going to state 2, what's the probability of going to state 3, what's the probability of going to state n. Let's say there are n states. Each row is just going to be a PMF. What's the probability of going to this state in the next round? Okay. So here's an example Markov chain where, let's say, these are the states. So for example, if you're in state class 3, then with 0.4 probability you'll go to pub, with 0.6 probability you'll go to pass, right? So this is just a Markov chain. Illustrate something. Let's not go into the interpretation of what it says. It's basically in the class, will you do Facebooking or not, and then maybe you'll go to next class and so on. You'll get some sleep. Sleep is the last end of day or something like that. So what are the sample episodes of it's called a student Markov chain. So what are the sample episodes of this Markov chain starting from a fixed state C1? So if you start from C1, there's going to be a bunch of states that you're going to observe, and that's going to be based on the Markov chain's transition probability matrix, right? For example, you can start from C1 and then maybe go to C2, C3, pass and sleep, right? You can go to 2, 3, pass and sleep. You can also do something else. In the sense, if you kind of follow the Markov chain, you may start from C1. If I go to FB, then maybe stay in FB, right? And then go to C1 again, then go to C2, and then go to sleep. Okay, you skip the third class, right? So there are all these trajectories, or these episodes that can come up, right? And if you actually, and this is the same transition matrix that you can use to describe the Markov chain. Like from C1, you can go to C2, and you can only do Facebook, and you can't sleep after that in C1 from C1. So it's just a description of a Markov chain. So Markov chain we are pretty familiar with. Let's add now a new ingredient, which is rewards. Okay, so Markov chain with rewards is called a Markov reward process. Okay, Markov chain is also called a Markov process, but it's kind of not very important. So what is a Markov reward process? A Markov reward process is going to, so previously we had states and transitions. That was a Markov chain. Now we're going to have rewards, so R's, that's going to be captured by this script R, and there's going to be a gamma, but it's not very relevant, so it's something related to discount. Again, the sums of rewards being infinity or not. This part is not very important. So S is going to be a finite set of states, P is going to be a transition matrix, and R is going to be telling me for every state, tell me what is the number that you can get. Okay. That number can be a random number, so I can take an expectation over that to call R subscript S. For every state, I can ascribe a single number, which is going to be the mean of some random variable. Okay, so I'm just ascribing rewards to states, which just means that for every state, I just put a, let's say these are deterministic rewards. There's no randomness. Let's say in this example, then I'm just adding these numbers into that graph in the Markov chain graph. Okay, now the Markov chain will still work as a Markov chain, so you will visit a bunch of states and so on. I can now define a new quantity, which is called the return. Okay, I'm gonna notate it by G subscript T, and it's just going to be, okay, the chain runs from S1, S2, S3 to ST. Then I'm just gonna capture all the rewards that I get from each of those states. Right? If I visit a state, at least in this diagram, I'm getting a deterministic reward of -2 or something like that. So I can do that summation, and I can do that for infinity. If the chain runs till infinity, if there is no conclusion, like in the example we have a conclusion, which is a sleep. If there is no sleep and the chain keeps on going on and on and on, then you need the discount to keep the summation finite. Okay, that's called a return. This is a random number, potentially, right? Because R's can be random, and so I'm going to define a value function. Which we actually saw 2 slides ago, according to these rewards, as is the expected return starting from state S. So it's just going to be V of S, which is going to be a number that assigned to a state. It's just going to be the expectation of a G of T given I start from state S. So G of T is just this thing. I just repeated the same thing of how I defined value function 2-3 slides ago, right? Or in terms of example, let's say we start from, again, state S1 is equal to C1, and let's say we have a discount 1/2. Okay, it's just arbitrarily chosen. Let's say this is the first episode or first run of the Markov chain. goes from, I always start from C1, or maybe not, so let's ignore this one. I always start from C1, so from C1, I went to C2, C3, pass and sleep. So in this case, I could have gone to Facebook, but I didn't do that. In this particular trajectory, I went from C1 to C2, and then to C3, and then to pass, and then to sleep. Okay, and then the value of that state C1 is going to be reward that I collect at C1 minus 2, reward that I collect at class 2, or the next state, which is minus 2, but discounted by 1/2, and then again next state minus 2, discounted by 1/2 square. That was gamma square there, plus the reward collected in the last state before the termination state, which is 10 times 1/2 to the power 3. Okay, it's just when I do the Markov chain, I visit a bunch of states. For each state, I have a number, so let me just accumulate those numbers, right? Weighted accumulation of those numbers. So that's a Markov reward process, and I can do that for various. So if I set gamma to be 0, which means that I'm not even counting. So value of state is just going to be the number that is associated with that state. So if instantaneous reward is 1, then the value of the state is 1, right? You can see that these two numbers are going to be same if gamma is equal to 0. That's just playing around with different numbers. If gamma is equal to 0.9, there are a bunch of other numbers, and if it's gamma is equal to 1, some other numbers. Gamma is equal to 1 can be set here because this doesn't. I mean, even if it loops, there is no infinite loop. Okay. And eventually, you will reach the sleep state. Okay. So now there's going to be an interesting twist, and which is kind of important to understand the Q-learning algorithm. So actually, a lot of things that we do in this explanation of this part is going to be a little bit hand wavy. So bear with it. Okay, so the value function can be decomposed into two parts. We can decompose it into an immediate reward part and a discounted value of the successor value of the successor state. Why is that? Because you can just replace the expression for g, which is the return, as this. Okay, there's no change there. Now I can take the gamma factors common, and I can get this summation, which is rt plus 2 plus gamma rt plus 3 and so on. But this summation is actually gt plus 1, right? So gt plus 1 happens when I am at state st plus 1, right? I reach some new state, and from that state I'm just counting the return. And then I can take this expectation is over all the randomness in the future. I can just take the expectation inside, some part of the expectation inside, and that's going to be b. Okay, that's just the law of breaking down the expectation operation over the succeeding stages. I have pushed that inside, and I've left the one which is relevant just on the outside. Okay, so that's what I mean by breaking down the value function into two parts: immediate reward and the value of the next state that I visit. Okay, that's which state I'm going to visit. It depends on the transition, and that's captured in this expectation. Okay, and I've just drawn this pictorially. It's basically the same thing. The expectation is just replaced by r subscript s, because we said the expected reward is going to be r subscript s, and I have explicitly written down the expectation operation. I'm in state s. There's some probability I can go to state s prime, and what is the value at that state s prime? This is just an expectation. Same thing. Yeah. So this is what is the recursion, some sort of a recursion, right? If I know this, I can compute this, right? So if you look at this Markov reward process, I computed these values, okay, using the infinite summation. Let's say I could also have computed this in a recursive way. In case I knew 0.8 and 10. Then I could have done immediate reward, which is -2, plus 0.6 probability of going into this state, whose value is going to be 10, and 0.4 probability of going to this state, whose value is 0.8. So you can get 4.3 like that. That's fine. Okay, so what is Markov decision process? That's just Markov reward process. A decision process is going to add one more ingredient into the picture, and it's going to be a set of actions. So we have a bunch of states, and we'll have a bunch of actions now, script A, and now the state transition is going to now depend on actions as well. So I'm in state S. The actions that I take also influence where I go, where I land next. Okay, So if I take a left, then with high probability maybe I should go left, and with some small probability maybe because of noise I don't go left, right? So the actions also should influence where I go in that Markov chain. Okay, and reward is still the same, but now reward also can be a function of the state itself as well as the action that you take. Okay, it's just an addition of one additional parameter, which is the actions. Now states and actions determine where you land next, rather than just state determining where you land next, right? So a slightly modified Markov chain from before, where let's say the actions are, if you Facebook, then you land in the state. If you quit, you come back to the state. If you study, you go to the state. If you study, you go back to the state. So now actions are in red, okay, and so now the rewards are tied to actions, okay. If I do Facebook, I get a reward of -1. If I study, I get a reward of -2. Maybe it's convenience factor or something. If I quit, I get a reward of 0, and if I really finish all the 3 studyings, I get a reward of +10. If I study, I can go to sleep or something like that. I mean, not sleep, but some state here. Okay, I just changed the names of the. There's no names for the states anymore. There's only names for the actions. Okay. So with actions, we can describe now. We can bring in the new object onto Markov decision process, which is the policy, which we have already seen before. It's just going to be the probability of a policy is going to tell me pick an action A with some probability given you're in state S. So that's an exogenous thing that I can now describe, right? And the policy can define the behavior of an agent. So in the Markov chain was just autonomous. I was not adding anything. It was just going from state to state to state to state, and it was generating a bunch of rewards. Now I have a control on. I can induce actions. I can do actions at every state, and now that's going to influence the rewards that I collect, and that's captured by a policy, right? I can describe a policy which will tell me what actions to take in different states, and therefore it will influence what rewards I collect as the Markov chain progresses, right? In fact, given an MDP and a policy pi, the state sequence is still a Markov chain or a Markov process, because condition, if I already tell you that for every state there is a deterministic action that you should take, there's no new information, right? If I know the state, I just look up what action I need to take, and so given state and action, I know which transition is going to happen. So it's like there is no any more degree of freedom, and so it's going to be just a Markov chain. Okay. And if you look at both states and rewards, it's just going to be a Markov reward process. So if I fix a policy, it's just going to be a Markov chain, essentially, is what we are trying to claim, or a Markov reward process. Okay. Now, any questions so far? Okay. Okay. So I've used this notation P superscript pi and R superscript pi is just to signify that if I have been given a policy, then I don't care about the full transition probability information where I was getting told, okay, if I'm in the state S and I take an action A, what's going to be the next state? Because my pi will tell me what action I actually am going to take. So I don't have to explicitly talk about an action that I'm going to take. That's just going to be what action does pi suggest, and given that action, where I'm going to land next. So it's just a convenient notation to kind of write superscript pi, because you're not taking care of actions anymore. Actions are not explicit anymore. Pi is completely determining the action, so there is nothing else to control in this Markov addition process. Okay, because pi can be it can be a randomized policy. That's why there's a summation here, but otherwise there's not going to be something like that. Okay, so let's again, the state value function for an MDP is the expected return starting from status and then following policy pi. So V pi of S is just fixing a pi is just a Markov chain, and we just talked about fixing a pi is just a Markov reward process, and we just talked about how this is computed, right? So that's what this term is, value function. But we can also define something called an action value function. Okay, so this is somewhat new now. So what is an action value function? The action value function is pretty much the same as this. This is the expected return starting from state S, but the first action that I'm going to say is not going to be according to pi. It can be something that I can control. Okay, pi is given pi. So what I'm trying to say is I'm in state S. I will suggest an action A, and given I'm in state S and action A, of course there's going to be some transition to some other state S prime. From that state onwards, just apply pi. So there is no more control there. If you apply a policy, there is no additional actions that I can choose, right? So that's all. So it's basically teasing out that the first action that you're going to take need not be pi of S. That's all. If it's not a pi of S, then it's under my control. If it's under my control, then I can pick any action here. And so for every action, I can get a number. So here I was just getting a number of one number per state. Here I can get whatever is the number of actions available at that state. I can get those many numbers, right? Again, policy pi is still fixed. So after I take an action, I just use the policy that I've been given. So that's fine. Okay, that's called the state action value function, and it's going to be very crucial in defining the Q learning algorithm, which is behind the Flappy Bird demo and all those Atari demo and so on. Okay. So similar to the decomposition that we saw in the Markov reward process, you can also decompose the value function as two parts: the immediate reward plus gamma times the value for a fixed pi of the next state. Okay, because for a fixed pi, it's anyway again a Markov reward process. So this is there's nothing major happening. This is just the same thing as Markov reward process. Now you can actually do this recursion even with action value functions. Okay, so what is it going to be? It's going to be the immediate reward plus q pi of the next state and the next action. Okay, given the current state and the current action. Okay, in fact, the next action is going to be pi of st plus 1. I didn't write it explicitly, but that's what it's going to be. So what I'm trying to say is the value functions can be decomposed as immediate rewards plus recursively can be written as functions of the next value functions from wherever you start. Okay, and there's a relation between the state value function and the state action value function, which is, as I said, I have one number here and I have potentially script A numbers here. Then I can just average them, and that will give me the state value function. Okay, there's just a very simple relation between the state action value function, which is a Q function, and the value function. Okay, this is just a diagram trying to say that V pi is Q pi is a function of both state and action. So let's say there are two actions, then the average of these two numbers weighed according to the policy will give me V pi. That's all. And similarly, Q pi it's a function of state and action. It's going to be the immediate reward plus gamma times the expectation of every state that I get to. So V pi of S prime, V pi of S double prime. If I get to these two different states, then the average of the value over there plus the immediate reward is my Q function. Okay. So these are just recursive equations trying to detail the value function. Okay. So you can write the value function. I mean, so this is just a very gory, full equation of the same thing that we were writing. So it's just the immediate reward plus the expectation over the next state's value function. Okay, where the expectation is over all next states I can possibly get to. That's captured by this expectation. So it's expectation. It's a sum because we are all in finite states and finite action setting. Okay, and similarly for the state action. Q function or the state action value function, it's again the immediate reward plus every possible state that you can get to, which is S prime, and from that S prime every possible action that you can take. That's going to be A prime. Okay, this is just an expansion of the V pi of S prime function. Okay, so there is just algebra. So these are just some recursive equations which are actually called Bellman's expectation equations. But so these are just very straightforward to kind of come up with. Now we're going to define what is called the optimal state value function, which is the maximum value function over all policies. So this is where we now try to change pi such that we can obtain a very high value for each state. Okay, so for any given state, I can maximize over all policies that I can possibly come up with to get to a highest number, right? And similarly, I can define the same thing for each state and action pair. I can maximize over all policies to get to a high number for every state and action pair. Okay, so these are the optimal state action value functions and optimal state value functions and state action value functions. And it so happens that for so if you can compute this, let's say we compute q star of s comma a. If we can compute this, if we can maximize this over all pi's, then the actual optimal policy is just going to be take that action which maximizes q star of s comma a and don't take other actions. Basically, it's saying if you had q star of s comma a, somehow you could maximize over all pi's, then you have all these numbers, then your optimal policy is just going to be, okay, I'm in state S, find the action that maximizes these numbers and play that action. Okay, so policy is just defined as a function of q stars. If I had access to q stars, I can just apply that policy. Okay, so so far we have just redefined. So we have defined value function, we have defined the state action value function, and we have defined that we have just said that they can be written recursively. Okay, that's the meta stuff that we went to in the past 5-10 minutes. And again, diagrammatically, how does it look like? So the value of a state, okay, is the expectation of current reward plus gamma times the future reward of the next state that we land. And this expectation is actually, if you draw it as a graph where the white nodes represent states and the black nodes represent actions, then all it's saying is that from this state I took some action A. After taking that action A, I went to state S prime or S double prime and so on. I just need to take an expectation, which is the average of all these outcomes. Okay, and similarly for the Q function, which is a state action value function. Okay, if you had access to this, now you use the notation, left arrow, to kind of signify that this is what I would have to do. So here we don't know both these guys and these guys, right? Those are variables. We don't have it. You could have solved if you write this for every state, then you have a bunch of such equations, and hopefully you can solve for the unknowns given those equations, right? You may be able to solve, you may not be able to solve, but given these types of expressions, we can actually intuitively kind of come up with a recursive algorithm, which is going to look like this. Okay, I'm going to start with some numbers for start with some value numbers for every state. Okay. And then I'm going to do update these numbers by this recursive equation. So actually I should write superscript. Let's say these are the new numbers and these are my old numbers. Okay, so these two are my old numbers and this is my new number. So I'm just saying that I can recursively compute these given previous iterations values. Okay, if I could get values at some iteration, I'm going to now define an iterative algorithm where I'll have a bunch of the value functions for every state. Okay, so let's say at iteration 10, I would have this number and this number. Using these two numbers and RT plus 1, I can update VST. Okay, in the 11th iteration. And one additional thing is we were actually supposed to do an expectation, in the sense average over all possible outcomes that are possible. All possible next states that I could get to. Instead of that, I'm just gonna sample one potential next state that I can get to. Okay, so instead of doing a summation to which was in the exact equation, I'm gonna take just one sample and I'm gonna represent that here. Okay, so that expression over there is nothing but saying b at some iteration k plus 1 at st is I'm gonna update it as 1 minus alpha times v k of st plus alpha times, instead of doing the expectation, I'm just saying I'll do RT plus 1 plus some gamma times some random state I get. Instead of summing over all states, I'm just doing taking one potential state that I can get to, I'm just taking that term. That's what that is. That expression is. If you take the alpha, I mean, if you can put the two terms on the right hand side in a single expression, then that's 1 minus alpha, this term here, and then alpha. So it's basically like a running average, okay, where I had some previous values. Let's say I had some previous values at every state. I just want to update to the next value, so I'll do one step from st. Maybe I'll get to st plus 1, and I'll get reward rt plus 1. I'll use those two to update my value at st. So this is actually called value iteration. And you can do something similar for the state action values as well, but which is what we'll get to, which is called Q-learning. Let me kind of stop the discussion about the basics like value function and state action value function, and say that these recursive expressions that we are looking at kind of lead to many variants of algorithms, okay, and we are not going to look at many of these other algorithms, but we are going to look at Q-learning, okay. And Q-learning, the name implies that we are going to deal with iterative updates of the Q function, which is going to be the state action value function, and the iterative updates are going to be very similar to what I've written here, and we'll just look at that. So any questions so far? We had to go through this so that we can easily understand Q-learning, but if you have questions, ask. Okay, so let's. So although what we looked at so far kind of gives you a different point of view for Q-learning. If you did not follow all that, that's okay. We'll look at Q-learning as a template algorithm as well, just like we looked at UCB or Thomson sampling and so on. So what is that? How does the algorithm look like? Okay, let's just look at the Q-learning algorithm. It's just a short algorithm, so let's look at it. Okay, so Q-learning algorithm is an algorithm to learn Q star. So eventually, remember Q star that I defined. There was this Q star of S comma A was the max over all possible policies. Q pi of S comma A was Q star S comma A in all my policies. And if I have this, I know what is the best policy, right? We just said the best policy is going to be argmax over A of argmax over A of this is going to give me the action that I need to take in every state. So Q-learning algorithm actually eventually computes this. It's an iterative algorithm, okay? Iterative algorithm just means that it's going to experience something with the environment. It's going to, take an action. It will get to some state, and it will get some reward. So the action that it took, the next state that it went to, and the reward that it got. So those three numbers or those three quantities, it will use that to update something called Q values. So it's an iterative algorithm. So at every round, it will maintain these Q values. These Q values eventually converge to this Q star of S comma A for every state and action. So you can think of Q star of S comma A as a giant matrix. For every state, for every action, there's a number, right? So Q-learning is going to do some iterative computation using at every round, it's going to use current state, next state, the action that it took, and the reward that it got, those four things, to kind of update the entries of that table, right? So, and that table is going to converge to this Q star of S comma A, where every entry is going to be Q star of S comma A. So it's an iterative algorithm which will converge to this, is what I'm trying to say. Okay?
So the table be a matrix for all states and all actions?
Yeah. Conceptually, you can think of it as a matrix with every row is a state, every column is an action, and so every cell of that matrix is going to be this Q star of S comma A number.
And one iteration will be one pass of the entire table.
No. One iteration is going to be, it's an agent, right? One iteration is going to be, I'm in some state st, I will take some action at, I'll get to next state st plus 1, and I'll get a reward rt plus 1. That's one iteration in the sense of that's one experience. I'm going to use that experience to modify one entry in my table, and I'm going to kind of repeat it over and over and over again.
So by the time you reach the end of the path, end of the whole path,
There is no path, right? So I reach at some other state st plus 1. Again, I'm going to start the same thing. I'm at st plus 1. I'll take some potentially random action. I'll tell you how to take the actions, but I'll take some action. I'll go to st plus 2, and I'll get reward rt plus 2. I'll use rt plus 2, st plus 2, st plus 1, and at plus 1. These 4 things to update one entry in my table. I'll keep repeating this infinity, and I'll actually show you. So let's start with state st plus 1. Sorry, s1. Okay, and for every time state, I'll first tell you how to pick actions. Actually, you can pick actions arbitrarily. You can in fact pick actions uniformly at random. Okay, 2 random actions. Q-learning is still figure out Q star of s comma a. Okay, that's the niceness of the algorithm. But let's see. Let's just say let's do something better. So it will take action uniformly at random with probability epsilon, very similar to the epsilon greedy that we saw. Okay, and then is going to take that action which maximizes. It's in a current state st, right? So I'm in some state st, and since I have the table at this iteration, I'll have some numbers in the table, right? So I'll take that action which maximizes over all a at this state a bunch of numbers, right? If I have 3 actions, I'll have 3 such numbers at this state, and I'll just pick the action with the highest number, and I'll play that with probability 1 minus epsilon. Okay. Once I've decided which action to play, I play that action, I'll land up somewhere at st plus 1, right? So next iteration I can land up at some st plus 1, right? And I'll get a reward rt plus 1, right? Those are 2 things which the environment will respond back. Now I'm going to use rt plus 1 and st plus 1 in this way to update my q entry at st and at. Okay, it's very similar to this expression. I don't know how many of you can see it. This also you can just write it as 1 minus alpha times q, the previous value, plus alpha times a new value. Okay, or written it this way, is just saying that the previous value is added a error term. It's called a temporal difference error. For some reasons, we're not going into the theory anyway. It's called temporal difference error, and alpha is just some constant, proportionality constant to keep things nice. Okay. So this is the update for that entry at st and the action that I took 80. Okay, and I do this forever. So epsilon is an explanation parameter, just like in the Epsilon Greedy algorithm for multi-bound bandits, and alpha is called a learning rate, very similar to we use learning rate in stochastic gradient descent, right? But anyway, so under appropriate assumptions, there are some assumptions that you need to make, which we'll not go into details of. It says that this table is going to converge to the Q star table. Okay. Formally, this convergence is called strong convergence, but we don't care. What I'm trying to say is that there's a table. I can maintain the table, and I can keep updating the entries by taking actions in this way and update the entries. And eventually, after a long time, I'll get a table where every entry is Q star of s comma a. And once I get that, I just play the action. I know what action to take once I have this Q star, right? I know I can just take the action precisely based on. I don't have to do exploit anymore. I just take the argmax of Q star of s comma a. Okay, that's Q learning. But to understand why this iterative update makes sense, and why this type of action selection policy or any other action selection policy can make sense, we need to understand a little bit more things, and we kind of skipped over those details. Okay, but otherwise this is pretty much. I mean, this update equation is very reminiscent to what is called the value function iteration. Okay, value iteration algorithm or value iteration update. But there are a few other things, details that we have skipped. So we will not be able to tell you formally why this makes sense, but this is the update equation for Q learning, and this is what is used in Atari, the agent that was designed for Atari games. Except they don't maintain a table, and we'll discuss that in 1 minute just now, which is as follows. Okay, tabular Q learning is not enough. If maintaining a table for every state, for every action, maintaining a number doesn't make sense because the states can be too many. Okay, for example, this gridded view. Okay, the real world is so the world is like this, But what the world is like this, and the position states are positions in the grid, then it's okay. I mean, you do forward, backward, left, right, just like we saw in the maze, and some rewards, and we can probably figure out how to get from A to B or whatever goal is. But in reality, what happens is the agent is navigating the real world, which is this, and it only gets to see the camera view. Okay, the states are not simple; they're not finite, or they are not small. There are many states. If you just think of the camera view or the snapshot, and that it sees it every time instant, right? So in this case, you can't really even write the table. I mean, there will be so many rows of the table, right? If rows are indexing states, so the agent which actually which actually was applied to the Atari learning environment, right? The breakout that we saw does something called function approximation, and so we will leave it. Just motivate what function approximation is and finish this class, which is instead of maintaining a matrix, which is the number of states times number of actions, which will have parameters which are these many in number, we will find ways to reduce dimensionality, because each of these numbers is like a parameter of this problem, right? Instead of computing all those numbers, I will represent that Q matrix using a function, okay, which will have its own parameters W. Okay, so what I'm saying is I'll have this Q star of S comma A, which originally was supposed to be a table for every state and for every action I was supposed to have a number. Instead of that, I'll have an approximation, which is going to be a function which is parameterized by W, which will approximately tell me what Q star of S comma A is. Okay, so it's like saying, given a statement in action, it'll tell me Q of S comma A comma W if there is a parameter W, and hopefully this is close to Q star of S comma A. That's all I'm trying to say. I have introduced an extra parameter W. Now, what are the functions that we can use? We can use any function. We can use a linear function, linear functions. Hopefully, if they can approximate these, so you can think of these as y's, right? And S comma A as features, and this Q stars as y's. If you can find a function which, given an S comma A, can approximate the ground label really well with low enough parameters, then that's what we're searching for. So you can use any function: linear, decision tree, neural network, basis functions, nearest neighbor, and so on. And specifically, neural networks are interesting. And the agent that was built for Atari learning environment in 2013 was actually using a deep neural network, actually a CNN, and we'll discuss that in the next lecture. So any questions about this? Okay, so just to summarize, RL is a great framework to make agents intelligent. You just have to specify goals and provide feedback. But there are many challenges that still exist. And in the next lecture, we will see deep learning function approximation based RL agents that show promise in larger complicated tasks. And so the representations that you get, when you forward pass the image through a VGG net, you got a representation, right? The 4096 dimensional vector. So those are what are representations, and they matter a lot in terms of how the agent can do well. Okay, human level performance, and there are very interesting applications. Yeah, so that's it. Thank you.